We're the University of Waterloo Robotics Design Team Mars Rover Division. Composed of over 40 students, we have access to our own workspace, machine shop, 3D printing center, and PCB manufacturing facility.
Our rover is a complex arrangement of subsystems including mobility, arm, power management, communications, controls, and science.
The mechanical subteam is at the end of a fresh design cycle that has elevated our rover's serviceability, modularity, and performance. One of our team's strongest assets is our robust chassis. A 2x3 foot frame of welded aluminum is supported by a differential rocker suspension system. With a maximum speed of 2 meters per second, the rover can surmount obstacles with suspension that can vary by over a foot. Chassis mobility will be improved in the future via increased wheel traction.
The basic structure of the arm is similar to the previous design, with 5 degrees of freedom plus an end effector. Worm drives are used to maintain arm pose while drawing negligible current. Electrical cables are routed through a hollow turntable shaft and wrist slip ring to prevent tangling and thereby increase arm mobility.
Designed to keep electronics enclosed and off the moving joints, the arm features a bottom-mounted board drawer to house all custom arm boards. The drawer can be removed independently of the chassis and offer complete access to team members performing maintenance or testing.
We are in the first stage of a 2-year plan to achieve autonomous science and claw end effector swapping. To accomplish this goal, the wrist link of the arm includes an end effector interface, which has locking cams to grab end effectors and 3 locating pins to allow for 1/8 of an inch misalignment. An inverse kinematics model is being developed for precise motion and intuitive operator control.
The software team has worked on developing, simulating, and integrating the rover's autonomous features. The rover is equipped with several sensors to help it navigate its environment, including a GPS, an IMU, visual cameras, and a depth camera. Gazebo simulation allows us to test our path planning algorithms on a platform with representative sensor suites and visualize the results in real time. Our autonomous navigation is broken into 2 stages, global planner and local planner. Our global planner dissects the route from start to goal into manageable GPS checkpoints. Our local path planner analyzes the occupancy grid generated by the depth sensor and performs dynamic window path planning towards the next global checkpoint. In the coming months, an algorithm will be tested to autonomously search for the tennis ball marker once the final goal is met. To detect the tennis ball, an image processing algorithm was developed using several different techniques, including color thresholding, noise reduction, and blob detection.
The team has designed its own PCBs and custom motor controller boards to control the rover's arm, end effector, limit switches, and science module. The boards were designed with a common component library with identical microcontroller pin designations to allow for more streamlined firmware development and electrical debugging. Onboard communication between the PC and microcontrollers is accomplished through a CAN bus for its noise tolerance and fault resistance. Both the base station PC and onboard PC are running ROS for reliable message transfer over our 900 MHz and 2.4 GHz networks.
The science team focuses on 3 main goals involving stratigraphy, sample collection, and experimentation. Sites will be analyzed to determine the prospect of its ability to support life. Panoramic views of the sampling site will be taken by a gimbal camera to establish geological deposition and evidence of the historical presence of water. Our science module is capable of extracting soil samples at a depth of up to 20 centimeters and store it in a closed container to mitigate contamination. The top 10 centimeters of soil is able to be separated from the desired soil via an actuated flap. Onboard tests will include moisture, temperature, and electrical potential evaluations. Further off-board scientific analyses include testing for amino acids, perchlorates, and pH. In collaboration with science departments at the University of Waterloo, access to laboratories and equipment has been granted for testing and competition purposes.